Good afternoon, everybody. Electric field, electric lines, and electric dipole. Here we will discuss about first of all electric field. What is electric field? Electric field is defined as the electric force per unit charge. Then we can define here electric charge. Electric charge is the fundamental intrinsic property due to which intrinsic electric force act. And the electric charge are of two types. We know proton as a positive charge and electron as negative charge, and both have same magnitude 1.6 into 10 power minus 19 coulomb. Here the unit of charge is coulomb, and the fundamental charge is the charge on the electron or proton denoted by small e, and the direction of the electric field is given by or taken by the direction of the force it would exert on a positive test charge. The electric field is radially outward from a positive charge, and we can say in negative point charge it's inwards. Here the electric field, here some group of fixed charges are there which exert a force by q test charge, and the force exert is from Coulomb's law. Then we can state Coulomb's law. Here we can state Coulomb's law. 2 point charges q and q test repel or attract each other basis of their charge nature is positive or negative. So Coulomb's law states that 2 point charges repel or attract each other with force which is directly proportional to the product of their magnitude of their charges and inversely proportional to the square of the distance between them. Here the distance between both the charges is r. So F will become by Coulomb's law F equals to 1 by 4 pi epsilon naught q test divided by r square, and here the direction of the force is radially outward, that's why here r vector. On dividing out by q test the electric field we get, and that is er equal to 1 by 4 pi epsilon naught q by r square r vector. Here also the electric field direction is same as force direction, that is radially outward falling off as a 1 by r. So here you can define as the electric field E is a force per unit charge that would be experienced by a test charge at that point. E vector is equal to F vector divided by Q test. This is a vector function of the position. Here some all diagrams are given: plus Q charge, minus Q charge. So in plus Q charge, here all quadrants electric field is outward, and in negative Q charge it's inwards to the negative charge. This shows the direction of the electric field, and in third diagram strength of electric field is given, and in fourth diagram superposition of electric field is happen. Two positive charge are there, plus Q charge Q1 and plus Q charge Q2, and we want electric field at point P. So we can put a test charge on point P, and that at point P it will experience forces and electric field E1 and E2, and by superposition them we get a resultant electric field E net. This is a superposition principle of electric field. Because the electric field is a vector quantity, that's why superposition occur. Now we will discuss about electric field lines. What is electric field lines? Is nothing but continuous line whose direction is everywhere that the electric field have. So if we take plus Q charge, then outward, and if we take minus Q charge, it's inwards, and the number of electric field lines is more, then we can say the electric field is more. And if the number of electric lines is less, means C outward, the number of electric field lines is rarer, then the electric field is less. If denser, then the field has greater magnitude of electric field. Some characterization is here. First point in the direction of the electric field, start at positive charge, end at negative charge. These are some electric field lines characteristics. Here some electric field lines are given. Two positive charge are given at right side C diagram. Here the electric field lines each other, they are repelling each other because they are same charge. That's why they are repelling each other. And they do not intersect each other. The electric field lines, they do not intersect each other. In B diagram we can see one is plus 2q charge and one is minus q charge. Here opposite charges are there. That's why they attract each other and the electric field line will emerge from plus q charge and end at minus q charge. Here also we can see at plus q charge, minus q charge, both are same but opposite in nature. Here also attraction plays at A diagram. Now we can see here the denser the electric field lines, more the electric field or electric field intensity. That's why at plus q2 charge the electric field is greater than minus q charge. Electric field lines at point charge, if any point charge is there, then electric field is a vector quantity and it's radially outward at point positive charge, and the line of force is given as the electric field line. Now we can see force due to an electric field. If any field is there, electric field is there, if we take any charge there, then that charge experience a force by electric field, and that is nothing but F equal to QER. Means here point Q that will exert a force by electric field, that is drawn by or made by plus Q charge. That's why plus Q charge will attract or repel the Q charge on the behalf of their nature of Q charge is positive or negative. If positive, they will repel, or if negative, they will attract. The electric field at R point in the direction that a positive charge placed at R would be pushed because they are both in same nature. That's why repulsion will be occur. Now we will discuss about the electric dipole. An electric dipole is consists of two equal and opposite charges, or we can say a system of equal and opposite charges separated by a finite distance or a less distance, minimum distance, that is called electric dipole. As shown in the figure, we can see both the charges have magnitude q and opposite in nature, minus q and plus q, and separated by distance d. And here we can say the electric dipole moment p vector of the system can be defined as the product of one charge magnitude and the distance between both the charges. And we can see the SI unit of electric dipole is coulomb meter. Here for Q coulomb and D for that is distance, that's why meter. So the SI unit of electric dipole is coulomb meter, and the direction is given by, here direction is little bit difference from electric field because electric dipole is formed, that's why is from direction from minus q to plus q, not from plus q to minus q. And we can see here in the diagram, the net electric charge on the electric dipole is 0. The net electric charge on the dipole is 0, but the electric field is not 0, since the position of the two charges is different, because the system of the charges are at different location. And here in this diagram, the electric dipole is situated at in an uniform electric field. What is uniform electric field? Where the electric field intensity is same at all point, or we can say everywhere the electric field intensity is at any point, we can take the electric field intensity equal. So by putting this dipole in electric field, uniform electric field, will the dipole move? Will the dipole move? Because the every electric field exert a force, so the dipole also exert a force by electric field. So the dipole move or not, we can see. What is the total force acting on the dipole? What is the force that will attract the charges to electric field? What is the force acting on this dipole? Zero force. Why? Because force on the two charges cancel each other. Both are same magnitude, that is QE right side and minus QE left side. That's why they cancel each other, and the center of mass does not accelerate here. But the charges start to move. Why? Rotate. Because the charges wants to be in an electric field, and the positive charge wants to be in direction of electric field direction, and negative charge wants in the opposite direction to the negative field. There is a torque because the force aren't collinear. Also here torque will apply, and force are in not collinear, means not in a one line. That's why here the dipole will move. And the torque is, what is torque? The multiplication of the magnitude of the force and the perpendicular distance between both the charges. Here the perpendicular distance between both the charges is d sine theta. D sine theta. And the direction of the torque in this case is given by the direction of the dipole moment, because QD is the dipole moment. That's why torque direction is also from the dipole moment. Here we can see, then the torque will be written as torque equal to P cross E in a vector form. Tau vector equals to P vector cross E vector, or in a scalar quantity, tau equals to P E sine theta, with an associated potential energy, that is U equals to minus P dot E. And here we can see the field due to electric dipole. Here one dipole is there, minus Q plus Q charge, and distance between them is D. At any point here it will exert a electric field, and by plus Q charge and minus Q charge, and we get E vector as net electric field. Some continuous charge distribution are there. Charge density by length, area, volume, and here we get the potential energy U equals to minus PE. Thank you. In next module we will discuss about the potential energy. Thank you.